Hello, everyone. We are here to talk about how we re-engineered Phoenix's query optimizer with Calcite. I am, where's the, oh, okay. Oh, okay. Yeah. I am Marianne from Intel. I'm a PMC member of Apache Phoenix project and also a committer of Apache Calcite project. And this is Julian Haidt here from HuntingWorks. He is VP of Apache Calcite. I'll start with the Phoenix project first, and we'll hand over to Julian once we come to the Calcite part. What is Apache Phoenix? Apache Phoenix is a relational database layer for Apache HBase. So first of all, it's a query engine that transforms SQL queries into native HBase calls, pushing as much as work as possible onto the HBase cluster for parallel execution to get high performance. It has a metadata repository to enable your user tables to work with the SQL type system. So it allows you to use DDL to either create a new Phoenix table or map an existing HBase table to, as a Phoenix table. So the table definition, along with all the other metadata information, such as view definition or sequence definition, are stored behind the scenes in these Phoenix system tables, which is essentially HBase tables. And starting from Phoenix 4.8, we are excited to have transaction support as one of our major features. And we also have table statistics, which are right now basically what we call guideposts. And these guideposts are collected behind us, in the background during HBase compaction, and are then used by the client to drive an efficient parallel execution on the service. I'm going to come back a little later to talk about how these statistics can be even more useful than that. And last thing is Phoenix is exposed on the interface level as a JDBC driver, so which means you can use it like any other JDBC driver out there. And let's also look at the advanced features. Either we already have or are on our roadmap. We have 3 different types of secondary indexes, the global and local index, as well as the immutable index. And we've been working all along to achieve strong SQL language compliance. And we'd also like to get some popular SQL extension features, such as window aggregates. And we also figured, it's nice to have easy integration or connectivity with other database component or big data components out there. For example, JDBC driver or ODBC drivers. So these are awesome features to have in Phoenix, but they've also created some architectural pain that has made us to think about, we need to have something new. So for example, right now we know that Phoenix does have some matching strategy to figure out if an index table should be used in place of a data table. So in this example, we have the data table called employees, which has the employee ID as the primary key, and also an index table, which is indexed on the employee names. So the first query is select from employee order by name, and apparently it should use the index table to avoid sorting on the names. And Phoenix is going to recognize the order by pattern is going to use the index table as well for sure. And the second query is select from employees, where employee ID is greater than 100. And this one obviously should use the data table, because that way we can drive a range scan. And also, Phoenix, and that's what exactly Phoenix is going to do by just looking at the world condition. But how about the third query here, which has both the where clause and the order by clause, all together? What are we going to do? So this is when we need to think. We need to have a cost. We need to make a cost-based decision. And so the statistics I just talked about are going to be very helpful here. So for example, we can get the number of bytes and the number of rows coming from either the employee table or the index table. And based on the byte count or row count, we can cost the table scan operation together with the sort operation, for either approach. And in the end, we'll be able to figure out which table is going to give us a overall lower cost. So this is our solution, Phoenix plus Calcite. Both are top-level Apache projects. The integration is going to involve changes to both projects. And the Phoenix part of the work is being done on the feature branch. Well, if there's any changes needed to the Calcite project, we've been pushing them into the Calcite's master branch. So the ultimate goals here is, first of all, to remove redundant code, especially in Phoenix's query parser and compiler, because we're going to replace it with Calcite's SQL parser and validator. And next is the most important thing is that we'll have the improved query planner, which does faster query planning, which produces queries that run faster. And also we'll have improved SQL compliance, and we'll also be able to get some nice SQL features for free, like the with clause, scalar subqueries, and the filter clause, which is pretty new. And so finally, of course, we'll have to achieve close to full compatibility with the existing Phoenix SQL and APIs. So we started this work around the end of 2014, and right now we are on a beta version. And so pretty much most of the query features are ready, and so we're looking to put this into a formal release by the end of this year. So this is the existing Phoenix architecture, which is pretty straightforward. If a query comes in, it comes through the parser first, gets converted into the parsnode tree, and then into an expression tree, and then it gets translated into a Phoenix query plan by the Phoenix compiler, and then the query plan will be executed on the Phoenix runtime. And you can see that everything here is pretty much very closely coupled. And also we have to do some query rewrites on the parsnode tree. And this is the original Calcite architecture. And unlike most of the other query engines, which usually go from parser all the way down to data access, Calcite actually is not bound with any specific data sources. So it's essentially just a query parser, validator, and query planner with pluggable data schemas, data storage, and customized data operators or optimization rules and customized cost model. So when we combine Phoenix with Calcite, we're actually plugging in Phoenix data schema and Phoenix data storage into the Calcite framework. And also, we're implementing a new set of Phoenix operators and Phoenix optimization rules and the Phoenix cost model. And the nice thing is, in the meantime, Phoenix can also inherit from the Calcite framework this ability of connecting to other data sources. So now that we know that we're going to have this cost-based query optimizer, but what does it actually mean in the Phoenix project context? So let's take a look at the existing Phoenix optimizations and features first. So first, Phoenix has done a whole lot of work in translating a key filter into a range scan or a skip scan, and also tries to optimize out the order by or push down, like sort or limit through union queries, etc. And also it has like different aggregate approaches plus different join implementations, and also does something to figure out like which of the existing data table or index tables is going to make the query run more efficiently. But as I said, Phoenix pretty much just uses static matching strategies to make optimization decisions, which are very limited in some use cases. And so what are we doing here with Calcite is we turn these features and optimizations into Calcite operators and rules so that all of these can be taken into account at the same time in this cost-based optimizer. And the optimizer can just file rules, numerous times as long as there's a match, and it's able to, figure out the best plan out of all possible combinations it gets from filing these rules. So, for example, as a result, Phoenix plus Calcite is going to do an even better job at filter pushdown or order by optimizations. So what does the Calcite algebra look like? So the query here is select products.name, count star from sales, join products using product ID, where sales.discount is not now, group by products.name, order by count star descending. So if you look at a diagram from bottom up, it's pretty straightforward, simple. So there's a join on top of the two table scans of products and sales. And after that, we have a filter node. And then we're going to do an aggregate grouping by product's name. And after that, in the end, we'll have a sort node on top of that. So our second example today is about one of the Calcite's built-in optimization rules called filter into join rule. We take the same query as in last slide, and the diagram on the left, which is before the rule transformation, is the same as from last slide too. So the filter into join rule actually matches the pattern of a filter on top of a join, which is the green node here. And then it checks to see if the filter is only going to deal with one of the join inputs only. And if that satisfies, the rule will be triggered. And so on the right-hand side, you can see a diagram, after the rule transformation, which is the filter gets pushed through the join node and moves onto the scan of the sales table. So now that we have some basic knowledge of how a Calcite rule works, we're going to go to the third example, which is about Phoenix joins. Right now we have two join strategies, the hash join and the merge join, and they both have their own advantages and disadvantages. And hash join is good when either side of the join is a small input, and merge join is good when hash join isn't able to do its job. But merge join can sometimes be expensive because it it can involve an extra sorting step if its input don't come in ordered on the join key. So we figure if first we can exploit the sortedness of the join inputs, and second, if we can exploit the sortedness of the join outputs, so we can make these join algorithms work much faster, right? And so this query is going to join the employee table and the department table together and order by the department number. And so as a first step, it gets translated into the Calcite logical algebra. There's a join on top of the two scans, and followed by a sort and a project. And next, this is this like planning stage. And we'll probably get a whole bunch of plan candidates, but the two listed here are the ones, the most promising ones, but with different join strategy. And candidate 1 is going to use the hash join, and candidate 2 is going to use the merge join. And candidate 2's physical algebra, turns to be a little bit different from the original logical algebra. That's because we have a rule called sort-remove rule here, which does its work when the sort input is already sorted. So originally there was a sort node on top of the merge join, another sort node on top of the scan of department table, and they got removed by this rule. And the only one sitting here is the one on the scan of employee table. So by comparing the two diagrams, it's easy to see that they have pretty much they all have project node, they all have scan, and they all have a join node, and these operators are going to cost similarly. And so the main difference here is the sort node. So candidate 1 is going to sort the employee table. Candidate 1 is going to sort the join output, while candidate 2 is going to sort the employee table only, which makes candidate 2 is cheaper here. And also based on a test on a 2 million row employee table plus a 2,000 row department table on a single node cluster, the second candidate actually saved 30% of the time. So this is the query plan on the left is generated by the old Phoenix, which is the same as what candidate 1 in the last slide would translate into. And also, we have an improved plan on the right, which is translated from candidate 2. And so this is a good demonstration of how we've been enabled by the Calcite framework to exploit the sortedness of both the join input and the join output. All right, let's go to Julian.
Thanks, Marianne. Can you hear me? Great. So Marianne has already kind of described by examples a lot of things that Calcite does. But I wanted to have a brief interlude and kind of explain what it is. It's a small Apache project. Because writing databases and query optimizers is relatively few people in the world do it. And I wanted to give a shout out to Apache. I mean, the Apache Software Foundation. You hear the word attached to various project names, but unless you're an actual committer, you may not actually know what it means and what it does. But it provides this environment where people from different companies, often competing companies, can work together without any mistrust. And we've got committers in Calcite from Hortonworks, and MapR, and contributions from Cloudera, and we'll get along. It's a superb process and community, and this kind of stuff wouldn't be possible without Apache. So, and Calcite, like all Apache projects, has a very open process. You can just show up on the dev list and start participating. So Calcite's been a top-level project since 2015. It's a query planning framework. I don't call it optimization because it's often difficult to get. It's almost impossible to get the optimal plan because you don't know everything about your data or everything about your query. So it's a kind of a toolkit, and the various people that participate in the project bring, they will notice they need something and they will bring it to the table. So the kind of contributions that have come into Calcite during this process have been, for example, I'm going to talk about this later, but improvements to Calcite support for materialized views, because Phoenix is the first project that has wanted to do optimization of secondary indexes by modeling secondary indexes as materialized views. So each project that uses Calcite makes it a little bit stronger and also shakes out a few bugs. It's packaged as a library, meaning you don't need to install anything on disk. You just embed it inside whatever engine you want to embed it in. You can use Calcite as a standalone thing, which with adapters, you can connect to it from a JDBC command line, but quite a few engines embed it. So Phoenix is going to embed Calcite, Drill, Hive, and so forth, include Calcite. It's kind of inside the box. And you may have seen my talk yesterday about streaming SQL. This is a kind of a new area, putting a SQL interface on top of streams and collaborating with projects like Flink and Samza and Beam and Storm. Okay, there's an interesting sub-project of Calcite called Avatica. It actually doesn't depend on the rest of Calcite, and one day maybe it will become an Apache top-level project. It basically solves the problem of, I've got a database and I don't want to write a JDBC driver and an ODBC driver for it. So it's a kind of wire protocol based on protobuf there's currently no ODBC driver, but there's a JDBC driver, and people have contributed drivers in Go and .NET so that you can easily build a JDBC driver. And Avatica is already in Phoenix production, and it powers Phoenix Query Server. So Calcite's a framework, which means it has a large collection of classes, APIs and SPIs. So brief overview. There's, on the left-hand side, we've got various classes that implement the relational algebra, so you can build a relational expression. You can either do that using the SQL parser, or you can actually build it directly using a class called RelBuilder. That's useful if you want to implement your own language. You don't want to use SQL, you want to do your own language. So the familiar things like table scan, filter, project are all in there. Metadata is a way of saying, is an SPI that you implement to tell Calcite, here are my tables, here are the columns, here are their types, and so forth. I mentioned Avatica, which powers the JDBC driver. Query transformation rules are the discrete pieces of functionality that together make up the planning process. So push filter through join rule was just one of those, and there's 100 or so more. And usually when people use Calcite for a particular engine, they'll end up adding half a dozen more rules, but they'll end up using a lot, the 100 existing rules as well. And one of the things Calcite does, it makes it easy to throw together the existing rules and new rules in a bucket, and it's very forgiving that it will just make all the rules work together. This is kind of an alternative to the anti-pattern, which is the handwritten optimizer, which is a 20,000 long method, if, which just breaks. And then pluggable cost models and statistics and so forth. So the planning process, it's actually got two planners, but the more complex one, the more interesting one, is based on the volcano and cascades work done by Gertzgraf in the late 90s, which is pretty much standard for cost-based optimizers. You first of all you produce a relational algebra tree, usually by parsing SQL. The system basically identifies, based on this tree, it does pattern matching to see which rules could possibly fire. Like, for example, if there's a filter on top of a join, then the push filter through join rule could fire. If that filter happens to be underneath another filter, then the merge filter with filter rule could also fire. So it basically just figures out all of the rules that could possibly fire and puts them in a queue and basically kind of sorts the queue to figure out which ones are likely to be most useful. And then it goes ahead and starts firing them one by one. And each rule, if it fires, may produce successors. The rules don't destroy their inputs, so after you've pushed that filter through the join, the filter on top of the join is still there. So it does only adds to the space of relational expressions. It never removes them, and it keeps on firing them successively, and it applies cost to figure out which is the best plan. So I wanted to talk about one of the many tools in the toolbox that Calcite provides, views and materialized views. Views are, I expect, familiar to most of you. Materialized views have a confusingly similar name, and in some ways they're kind of like views backwards, which I'll explain. The reason I want to talk about materialized views is because Phoenix uses them to do secondary index optimization. So a view is an expression, a named expression that gets expanded like a C macro when you execute a query, when you're preparing the query. A materialized view is an equivalence between a table, which is populated with data, and an expression. And the idea is that in order to use a view, you need to reference it in your query. A materialized view, you can reference it in your query if you want, but you don't have to. In fact, if you write a query that is somewhat similar to the relational expression that matches the materialized view, the planner will go, I could use that table, which has 100 rows, rather than reading the table their query is talking about, which maybe have 1 billion rows in it. So it's potentially a huge performance optimization. So here's a query using a view. Just wanted to show how view expansion works. So at the bottom is the view, managers, which is all employees that have someone working for them. It's a self-join. And then at the top is a query that the user has written using managers. So, and on the right-hand side, I've converted them both into relational algebra. So you see the scan of managers, which looks to the SQL parser looks like a table. We're going to expand that, which basically means we're going to substitute this tree at the bottom in where managers occurs. So like that. So that's what happens after view expansion, and probably the first step in the optimization process is going to be, spotting this filter, and this can be pushed through the project, which is almost certainly going to produce a plan of lower cost. So contrast that with materialized views. Calcite doesn't actually support this syntax, but it gives you an idea of what it's doing. Is it's associating this query, select depth, no, gender, etc., and with this name, emp summary. And here's a query at the bottom, which is not referencing emp summary. It's actually referencing the emps table, but it's doing an aggregation on department number. So, so it's possible to satisfy that query by reading the emp summary table. And to use it, Calcite basically has to rewrite the query so that the relational algebra of the user's query, which is at the bottom there, exactly matches the relational algebra of the summary table, or at least a part of it, one of the leaves of the tree, exactly matches. And that's a hard thing to do, but Calcite kind of works backwards from what it's trying to achieve and does kind of unification to achieve this. Once it's achieved it, now we can safely substitute the emp summary table into that query, like that, ta-da. And we've now got a plan which is much lower cost. So I'm going to hand back to Marianne now, and she's going to explain how we use this materialized view mechanism to optimize secondary indexes.
Can you hear me? Yeah, Julian just explained how materialized views work in Calcite. So we just look at this example. I mean, like, you know, how Phoenix uses it to solve the problem of matching secondary index. So right now we have this secondary index table, which is indexed by the department number, and I mean, in terms of the semantics of secondary index in Phoenix, it's just, I mean, like a table that is ordered on a different dimension, right? And so they can be, I mean, described as select, you know, like select department number, employee number, and name from the employee table ordered by department number. And after like the substitution on the I mean that, you know, that is applied on the left of the tree, it becomes something, you know, like that is shown on the right, and which can exactly match the view definition here. So this one eventually is going to be replaced by the scan of the index table. And so when we look at, you know, like, so these are actually, I mean, before substitution, you know, which uses the original data table, and after substitution, which uses the index table. So these are actually parallel plan candidates. So, I mean, a substitution doesn't actually mean that we're going to use the index table eventually, but it just adds another whatever candidate to the selection list. So we're going to compare the cost on both sides, and apparently, you know, like the left-hand side is, you know, for example, if it produces like 1,000 rows from the employee table, and the filter is, you know, the filter is going to filter on these 1,000 rows, and after the filter, maybe like one-fifth the rows are going to come out of the filter, and the project is going to project 200 rows, which costs like 200 something. And then, you know, in the end, you know, if we cost the sort node as n log n, it's going to be like something like, you know, 1,600. So this illustration of the cost is based on, you know, very simple, you know, like the, you know, very simple strategy on the row count, but actually it doesn't work exactly that way, but it's just a good illustration of, you know, how we cost them. And also on the right-hand side, we have like also if we do the scan of the employee, the scan of the index table, it will be exactly the same count of rows that come out from the index table. So again, it's 1,000, and a filter is going to filter on these 1,000 rows, and after the filter, it will be like 200 nodes left. 200 rows left for the project to do its job. So apparently, you know, like just looking at the diagrams, we can figure out like there's the sort node is not present on the left-hand side. So basically, we are saving the cost of sorting. And, you know, so this is a good illustration of, you know, how Calcite first substitutes the original query with materialized view candidates if something can be matched. And they're both like thrown into a selection list, and all the decision in the end is just made by costing all these candidates. Yeah, so let's come back to the. Oh, sorry. Oh, okay, sorry. Yeah. So aside from this cost-based optimizer, we also have some other very significant benefits from doing this integration with Apache Calcite. So first of all, as I mentioned, we are going to achieve good SQL language compliance, and also with a couple of nice SQL extension features. And next is this materialized views I just talked about, and also Calcite supports materialized views of all various kinds. For example, from a filtered view to a aggregate view or even a joint view. So this is kind of giving Phoenix the opportunity of support different types of indexes in future. And also, very importantly, is this interop with other Calcite adapters. It's just easy or even effortless for Phoenix to connect to these adapters, such as Hive, Kylan, or any other JDBC sources. And talking about connectivity, we have in fact implemented an initial version of Drill and Phoenix integration, and we call this Drillix. And thanks to the fact that both projects now work on the same Calcite relational algebra and under the same query planning framework, Drillix is not only able to just dedicate the table scan to Phoenix, it's also sophisticated enough to push part of the aggregation job or even part of some other coprocessor job down into Phoenix runtime. So in this example, we'll see how Drillix will work out a group by query. As the first step, Phoenix will do the table scan and the first part of the local partial aggregation, and it will hand over the results to the drill side, and drill will convert it into the drill's own data format, and we shuffled across drill servers, and then drill will do the final aggregation. All right, thank you very much for coming to our presentation. Any questions? Yeah.
Mine's probably a really dumb question, but we're just now looking to use Phoenix on HBase. With these big changes coming, would you recommend people that are on the cusp of getting started to wait until early next year, because you're rounding out some of these things that you said would be done at the end of 2016?
I wouldn't think so, because the interface won't change anyway. It's just, this is all happening behind the scenes, so you don't really have to worry about. For some use cases, it actually will do a lot better. For example, it will generate a whole different query plan. But for other use cases, for simple queries, it won't make any difference that you can observe. Yeah.
Thanks.
Sure. Yeah.
Why should you go for Calcite? You can optimize Phoenix itself, right? Yeah.
Sorry?
You can optimize Phoenix itself. Why to come up with the other project?
Well, good question. So, it will require us to implement, otherwise it would require us to implement a whole new thing, just like Calcite. So why wouldn't we use Calcite?
Can I chime in here? Writing query optimizers is really, really, really hard. Okay? You can write a bad query optimizer. The key to cost-based optimization is that this idea that when you apply a rule, you don't destroy the tree. You keep the old copy. Because it's the classic optimization problem of local minima. You may think that pushing this thing down here improves, but you fall into a local minimum. So you have to keep what looks like a worse plan and fire all the rules on that apparently worse plan in order to be sure you find the best plan. And the secondary index substitution is an example. As Marianne said, we have the initial query that uses emps, and we have another query that uses the index on emps. We optimize them both. We consider both of them in parallel. A simple handwritten optimizer can't do that. Yeah, the Volcano framework is a very sophisticated piece of work. I didn't invent it. And Calcite's an implementation of that. So, by moving to this, Phoenix is getting rid of code. It's the most important job of an architect is to get rid of code. And James Taylor started this decision going. So now there's a whole bunch of code in Phoenix which does not have to be maintained. That's just awesome.
And also I mentioned that, we've been working very hard to get the SQL compliance we need. And that thing, has taken us for how long? Since Phoenix started. And just having Calcite is just, you don't have to do the work at all from this point. Yeah.
Okay, looks like our time's up. Thank you all.
Thank you.
And we'll be around if there's any more questions. Thank you.